So probably great. Okay, we're recording now. So this is a project that we've been working on with the team, mostly Google Research over the past, I guess maybe the past 3 or so years, on an approach that to sort of for modeling the Earth's atmosphere with a combination of AI and sort of traditional simulation methods that we call neural GCM. So this is again a large team, mostly sort of my collaborators at Google Research, but we also sort of advised by some folks at ECWF, MIT, and at Google DeepMind. Okay, so here's kind of the outline. I'm going to talk about kind of the recent revolution in AI weather forecasting, which I think there's been some talks on before in the seminar series. And then kind of get into what we've been doing, which is sort of hybrid physics and machine learning models, and then talk about our results on both ensemble weather prediction and climate modeling, and then sort of close with some discussion of kind of like the bigger picture and kind of where some of the questions that I hope that we're able to answer sort of in this field going forward. So first, let's talk about the AI revolution of weather forecasting. So first, to understand how we've been doing weather forecasting over the really for the past let's say since the advent of numerical weather forecasting in I guess roughly the like the last half of the 20th century, we've been doing weather forecasting with sort of physics-based simulations. And that begins with sort of understanding the sort of like the equations of the Earth's atmosphere and sort of other parts of the Earth system, sort of going back to Richardson and others in the early 20th century. And this program of sort of simulating the atmosphere with sort of detailed physical simulations has actually been quite successful over time. There's this really nice review paper by Bauer and some folks at ECWF, where they chart like the progress, the skill, the weather forecasts over the past 4 decades or so. And what you can see is that the accuracy of weather forecasts has been increasing over time, about 1 day further into the future per decade. And so that means that the weather forecast of 1980, we can now do the accuracy of what was a 3-day weather forecast in 1980 is sort of approaching the accuracy that we have now for a 7-day weather forecast. The line's actually moved up a little bit since this paper almost a decade ago. And so that's very impressive, sort of slow iterative improvements. And now the weather forecasts work pretty well. These are like the weather forecasts we use. Well, in just the past couple of years, we've seen sort of a new approach to weather forecasting that has sort of suddenly become actually really successful. And so here I'm charting the progress of different weather forecasting models over the past couple of years, and I'm charting them relative to the skill of the ECWF forecast model, which is generally considered the world's best forecast. This is their sort of deterministic forecast. And if you look at the skill of these models in sort of the first few attempts at this back in like 2019, 2020, they had about twice the error that for a few day forecast, those but like almost those over like twice as large as the ECWF model. So like really it's interesting, intriguing, but like definitely not there yet. And then something changed in 2022, and suddenly there were a few models starting with this work by Ryan Kiesler with the graph neural networks, and then work from a team at Huawei that used transformers called Pangu, and a team at DeepMind, sort of GraphCast, that suddenly they had models that all of a sudden actually sort of hit this accuracy threshold of the world's best numerical weather forecasts, and potentially actually sort of shot above this in some ways. And so this was something, and so this I think has really caught the the weather community, sort of I think by surprise. So there's been a lot of excitement about this, and institutions like ECWF, which makes a numerical forecast, has now invested very heavily in building their own AI weather forecasting system. Organizations like NOAA as well in the U.S. are sort of very spending a lot of effort on trying to build their own AI forecasting systems, or at least figure out how to use these AI forecasting systems to improve what they do. And it seems, I think, very clear here that this is the AI weather forecasts are going to be a very big deal. Now, of course, these systems can make sort of really accurate predictions. They haven't sort of fully solved the problem yet. And one way I like to look at this is think about this GraphCast, which is currently kind of one of these close to sort of state-of-the-art weather forecasting systems, and compare a simulation over this is a 10-day forecast. This is of atmospheric humidity versus ERA5, which is typically the ground truth used for training these data sets. It's a reanalysis data set. And what you see is that ERA5 has these very sharp features that keep on, especially in the tropics, where you sort of keep on seeing these different like storm systems emerge and all this sort of variability from over different hours of the day. But in GraphCast, as you go out to sort of for longer and longer lead times, the model, it actually gets sort of progressively blurrier. And that's partly sort of a detail of how these models are trained. They're sort of optimized to try to predict like the average weather, and in the face of uncertainty, the average weather sort of looks the best prediction of average weather is pretty blurry. So these models are are remarkably skillful, but they're not yet entirely physically realistic, and that's kind of the problem that we try to address in this work. Really trying to focus on how we could make how we could make a sort of weather forecast and sort of take the strengths of these new AI weather forecasting techniques, blend them with sort of like some of the strengths of sort of traditional physical modeling approaches, and hopefully make progress on some of these challenges with physical realism that are important for a lot of use cases, like predicting extreme weather or climate modeling, where you really average weather is sort of not enough. And kind of like in this sort of this blurriness kind of like blurs out all the interesting details of weather and climate. Okay, with that, let me get into hybrid modeling. So why consider these sort of hybrid machine learning and physics models? Well, I like to think of this in terms of kind of looking at the extremes and kind of looking at what this hybrid synthesis can offer potentially. So on the one side, we have these pure machine learning techniques. And here, I guess, a couple of these models like GraphCast and Pangu. And these models are typically created using all these approaches now are using deep learning. They're sort of giant neural networks. There are a few different architectures that people have used productively, like graph neural networks or different transformer architectures. And these, and then in contrast, we have sort of the more traditional physics-based simulations, which again are discretizing PDEs and the other equations of the Earth's atmosphere and the Earth system on a grid. And this is again how traditional numerical weather prediction and climate modeling works. So the machine learning approaches have some interesting strengths. First of all, they are a lot less code. They're a lot in some sense, they're a lot simpler than the physics-based methods. Like GraphCast is about 5,000 lines of code, at least to in terms to define like the trained model. They're optimized directly to make the most accurate forecasts. And they're really based all on the data. You don't need a lot. There's not a lot of sort of physics-based modeling that goes into GraphCast. There's just there's some some of the prior structure of weather is kind of built in to how the neural network architecture, like say if it's on a graph, there's some notion of locality, or that things should be defined on a mesh. So the model does predict the like the weather state on a grid in terms of the different 3D variables, different levels of the atmosphere, and sort of the different physics-based variables from these simulations. But it's really a very empirical approach, and it can be optimized very directly for the accuracy of the forecast that you sort of care most about. Like, say, what is the weather forecast over, say, a few days in the future, and everything is tuned for that. And in contrast, the physics-based methods are, well, first of all, they're much more complex. In terms of like the number of lines of code, there may be hundreds of thousands, millions of lines of code. The strength, though, is that these methods are much more interpretable. So we can break down all these different physical processes, and we really can understand at a very high level of detail. So instead of the complexity being so there's sort of complexity in terms of all these different processes versus complexity in terms of maybe a bunch of neural network parameters in a small number of lines of code. The physics-based methods, of course, are based on the laws of physics, so generally principles that we understand pretty well and we believe in. We don't really need, for the most part, we don't really need data. And the strength of that really is that the physics-based methods are something that we believe will generalize to different settings. That's especially relevant, for example, in a climate change context where we don't in like a climate change context where the maybe we want to do this like in a climate projection. We don't have data for what the Earth is like with twice the level of carbon dioxide. So we have to think. So it's not clear how the sort of pure machine learning approaches can sort of possibly solve that problem. And in between are hybrid models like neural GCM. And so in these sort of hybrid modeling approaches, what we do is we take the parts of the physics-based models that we believe in, say like simulating the large-scale patterns of the Earth's atmosphere. But there are some parts that say that there's more uncertainty about, sort of more empirical models, and that's typically at the sort of beneath the grid scale in a climate model. So processes like clouds and rain, solar radiation, and so we're going to use the AI components sort of inside the physics-based simulation in these hybrid modeling approaches like neural GCM. To sort of correct the small scale errors, while hopefully still retaining some of the generalization properties and the strengths of the large scale simulation. Okay, so let me talk a little more about hybrid models. So this is not a new idea. There are some of the first work on hybrid models is, dating back to some dating for over 5 years. It's been, I say, hybrid modeling has been there's some preliminary efforts. I think were pretty encouraging, but there's been a lot of groups that have been working on this, but it has been a pretty challenging road for hybrid modeling. And in particular, the challenge is that oftentimes you train these models. You train these models, and they actually they have very poor results when you run them. When you try to do a climate forecast with them, you run them, and the model blows. Maybe the model is stable. It can only make a forecast for maybe some number of months or maybe some number of hours even. And in a lot of cases, some teams have worked sort of very hard on this and actually gotten some sort of reasonable results, but mostly in sort of more idealized settings. And the improvements that we've actually seen from doing this, even though in principle this is where all the error, we very strongly believe this is where the errors in climate models are. The actual improvements that we've seen from the hybrid approaches have been much smaller than the sort of improvements that we've seen with like the pure AI approaches. Nothing like that dramatic sort of reaching parity with the best physics-based simulations. So what has gone wrong? Well, one thing that sort of our hypothesis sort of going for this work is that one challenge with these hybrid models is they're typically optimizing the wrong metric, and they're doing something called offline learning. So I'm going to tell you what that is and why that's problematic. So in the offline sort of learning model for machine learning, we're supposing that we have some part of the simulation that we want to keep that we believe in, say solving laws of physics. In this case, let's say this is the dynamical core from a weather or climate model, but it could be some other part of simulation. And this answer is like pretty good. It's pretty close to what to predicting how a system should evolve. It's solving sort of most of the equations, but we know that there's stuff that's not solved in the simulation, and we know the simulation makes errors. So in the offline modeling approach, what we do is we collect a bunch of examples. We take sort of the state of the system. Let's say, for example, some time what happens. You put it through this dynamical core, and then it produces an answer here. This is like the input into the neural network. or some other AI model. And we have also collect a bunch of outputs or desired outputs of like what we think the model should produce after sort of stepping forward for a time step. And so now we have a bunch of input output pairs. We can kind of do the standard the standard machine learning thing and so we can train a neural network, we can train a decision tree or do gradient boosting, any of these other machine learning techniques that that the machine learning community has been tuning for a very long time now. We can train a model, and we can use it to make predictions about sort of the updated state of the system, just correcting the errors from the previous step. So the problem here, again, we train this because we have these input output pairs. What we're doing is we're optimizing the model to make predictions one time step into the future. Or for example, we might be optimizing maybe not even a full time step, just optimizing, say we want to calculate maybe a flux term from a model, and we have some sort of labeled outputs, we have inputs, and we're trying to predict those. But it's actually pretty different from how we want to use the model. So in practice, when we want to use the AI model that we trained, we want to plug it in repeatedly over many time steps. And that's because in say a climate model, for example, you're running things out over thousands, maybe tens of thousands, hundreds of thousands of time steps. Each step is like, maybe plus an hour, plus some fraction of an hour in the future, and you want to run the model for years. And so there's a very big difference between how you're training the model and how you're running inference or making forecasts for the model. And this gap, this discrepancy between the training and sort of the validation setup is something that in sort of the machine learning community knows to be sort of potentially very problematic, because you've optimized the model for say a very short time behavior, and what we actually care about is very long time behavior. And so this gap means that in practice, these models often don't perform very well when you run them at sort of many time steps. And that's because you can get these feedback cycles that appear where errors get amplified when they get sort of the neural network makes certain types of errors, which are different from the errors that are made that are seen during training. And the sort of when training, the model never sees the errors that are made by the neural network, so the changes in the state. And these systematic differences can cause often very large errors to build up over many time steps. So what we did is something a little different. So we kind of went back to the setup here, and we decided, let's see if we can optimize through this entire process. So not just optimizing the neural network, but also optimizing the physics-based simulation through the physics-based simulation as well. And to do that, what we had to do is we had to take that dynamical core and we had to rewrite it in a programming language that has support for differentiating through the dynamical core. So now we can do sort of gradient-based optimization through the entire coupled system, not just through the neural network. So we did that in JAX, which is a Google framework for writing deep learning models. It's used by sort of almost all of Google's models these days. Like tools like Gemini, for example, but also could be done pretty straightforwardly in PyTorch or Julia. So now we have the differentiable dynamical core. That means that when we train and run inference, in both cases, we can now have a setup where we can be training over many time steps. And so we can optimize the behavior of the system to match some desired set of observations. Again, even after feeding it through many times, because we're able to take optimization steps through the entire trajectory of a many time step weather forecast. So that's kind of set up. We call this is known as a sort of a online training, because the setup matches the training setup matches how we're actually going to use the models. Okay, so with that, I'll sort of introduce what we did with Neural GCM. So this is a differentiable hybrid model for the Earth's atmosphere. So again, the structure here is that we took a dynamical core for the Earth atmosphere. We used spectral methods, which are kind of a standard technique for simulating for atmospheric simulation. And we combine it with a neural network just to solve the parts of the the parts of the system where there's sort of a scientific sort of uncertainty about the right way about how to model sort of the small scale physics. Here, this is like the physics in a climate model versus the dynamics. Sort of confusingly, the physics is only part of the physics. And then we're going to train these models on making weather forecasts up to sort of 3 or 5 days from this reanalysis data set, which is this sort of historical reconstruction of the Earth's atmosphere over at a high resolution in space and time over the past 40 years or so. And so the high level structure of the model, I'll kind of walk you through this, is that we have the sort of the 3D state of the atmosphere, which are different variables like wind, humidity, different like sort of liquid and ice water, sort of clouds and temperature in the 3D atmosphere. We also have forcing variables, which here are the sort of solar radiation at the top of the atmosphere and the temperature, the sea surface temperature, and the extent of sea ice. And then we also have sort of correlated random noise that we also sort of put into the feature into some of our models. So we have, these are kind of like the inputs. We want to predict the outputs that are like, again, these 3D atmospheric variables sometime into the future. And so the first thing we do is, so our inputs are actually we have our inputs that these are on a slightly different grid system than our simulation model. So we have this encoder that translates into from a different coordinate system, from a pressure level to a sigma coordinate. And then our model itself is a combination of this, again, the physics-based dynamical core and the learned physics, which is going to be a giant neural network. It's going to deal with stuff like the clouds and solar radiation and so forth. We are still solving this in the context of a differential equation solver that's kind of stepping forward for, say, stepping forward some number of minutes, or maybe up to like half an hour or so, a bunch of little time steps into the future. And then eventually we have the state of the system, some number of time steps forward, and then we kind of decode it back to these to the variables sort of on the grid system that we want to predict on. So that's the structure of neural GCM. I can, if people have questions later, I can kind of go into more of the details, or you can look at the paper. We talk about some of the results. So first, I want to talk about the results for ensemble weather prediction. And so first, so something that we're sort of very happy with here is we have a model that can beat this ECWF model for ensemble weather prediction. And I want to sort of talk about, maybe for those of you who are not extremely familiar with ensemble weather prediction, maybe take a step back and tell you a little bit about why ensemble weather prediction is a really big deal. So basically, ensemble weather prediction is kind of like it's essentially like the only way to do weather forecasting well on a time scale of sort of beyond a couple of days in the future. And that's because there's uncertainty about the state of the about the sort of the state of the atmosphere and the Earth system. And if you just make especially with a traditional physical simulation, if you make a single simulation of what might happen after about, like, especially like a week, 10 days, there's so much you're really making a lot of your simulation is making pretty arbitrary choices based on sort of that could be perturbed by sort of very small errors in the initial conditions of the weather forecast that could really throw things off. So what all sort of these sort of weather forecasting centers like ECWF do is they run ensembles of weather forecasts. They run, for example, about somewhere between 10 and 100 simulations of different plausible weather conditions based on adding random noise to the sort of perturbing the evolution of the system, perturbing the initial conditions, and that makes a much better weather forecast. So here I have the top, for example. These are the two models I showed you earlier. There's this orange line is the high res forecast, a deterministic forecast from ECWF, and the green line is GraphCast, which is that AI model that had like the one I was showing you earlier that had like results that were actually better than the deterministic forecast. So it's impressive that it's better than the deterministic forecast, but they didn't really solve the problem. In the sense, it was actually still much worse than the ECWF ensemble forecast, especially if you go out beyond about sort of about 5 days in the future. So the silver line here is the ensemble forecast from ECWF. And here we were able to, and so this is kind of the milestone that we were able to hit with the ensemble version of neural GCM. Again, because we sort of inject the random noise, we're in a both the initial conditions and the evolution of the system, we were able to make a forecast where the average of a bunch of simulations was better than at reproducing. Here's the sort of 500 millibar geopotential height, which is what meteorologists like a metric meteorologists like to use to look at weather forecasts. We're able to beat that the sort of best ensemble-based weather forecast. And we can also compare on there's a bunch of different metrics, but things like a CRPS is like a score that people use for probabilistic forecasts, and we're also able to sort of exceed this best physics-based forecast. Okay. But we can go to a very long list of metrics. So this project that I sort of took part, I also helped on, called WeatherBench 2. If you're curious to see kind of like the full lineup of these different AI weather models, there are a bunch of them now. But right now, the neural GCM is the top model on the WeatherBench 2 scorecard. Okay, so I'm going to. This is like a bit of a challenge for the audience. Maybe you can. I'm going to try to wake you up and see if you can think. Sort of like take a look at these forecasts. And so what I've done here is I'm showing some simulations. These are each of these. So two of these movies, or one of these movies is what really happened. From this ERA 5 data set. I've sort of made it a little more challenging. So I put them all in the same. I've resampled them all to the same grid resolution. And two of these are forecasts from our neural GCM model. And I'm going to ask you to pick which of these options A, B, or C is sort of what really happened. It's like the ground truth. So you can look at the movies, and I'll show you I'll show you a few frozen frames next. So first, let's take a look at what happens in a 5-day weather forecast scenario. So this is sort of going out 5 days in the future. All of these are actually this scenario I picked. This is a tropical cyclone hitting the Gulf Coast of the United States. They all kind of have the hurricane hitting at about the same time. The large scale patterns look pretty similar. There's a bit of variability in the tropics here, where it's sort of like where you see like the details of the weather patterns are different. If you go out to plus 15 days, now they've kind of diverged off in different directions, but they all look like plausible weather in different ways. And it's, at least to my eye, it's a little hard to tell which of these is actually which of these is actually real. They all have the sort of, you can see like these weather patterns through the tropics. You have the intertropical convergence zone. They all have some things that look like maybe something like an atmospheric river that's heading up somewhere towards Alaska. Okay, so maybe take a moment to make your guess. I won't make you say it out loud or raise your hand because we're not on a live audience. Well, we don't have you're not in the same room. But which of these three is real, A, B, or C? The answer is that C was real. And if you look really closely, there are kind of a few little glitches a few things that sort of show it. I think the most obvious thing is that it's slightly higher resolution, and you can see that kind of in the tropics here. And our simulations are sort of not fully resolved at this grid resolution, so they're a little bit smoother. But it's pretty challenging to tell them apart, and we're getting pretty close on this AI weather model sort of Turing test. And this is pretty encouraging actually, because this sort of consistency is what we need to use for weather model, AI models for sort of going beyond weather to like applications like climate or studying other sort of physically realistic parts, sort of other parts of the Earth system. And so we can do things like with this, like track, like look at the ensemble forecasts of hurricane tracks. And here's just a comparison of, this is a 5-day forecast of where, this is a hurricane from 2020, Hurricane Laura, where it might end up. And you see, at least at a high level, the forecasts from from Neural GCM and the ECWF model look pretty similar in terms of when you run the model 50 times, they all show up, they all sort of a similar degree of uncertainty about where the hurricane might actually be and how it compares. Here, the black line is the ground truth of where it actually went over the course of these 5 days. Okay. And yeah, and the other, again, big strength here is this model, of course, is these AI models are much faster and much cheaper. So this is kind of like, these are kind of like ballpark numbers. I don't have an exact number for how much a single ECWF forecast costs. But this is like sort of ballpark for one of the 50 ensemble members. It's something like, they do this like, again, like 4 times a day. And so it's pretty expensive. They have a big supercomputer running this, and like making all these forecasts with Neural GCM is like dirt cheap, just paying literally pennies. And it's a lot faster. You can run it something they can run in sort of like under a minute for these weather forecasts. So potentially we could run, say, much larger ensembles, and if you wanted to like really quantify uncertainty or really concerned about like the risk about what exactly is the chance that a hurricane, not just where might a hurricane hit kind of in general, but like what really is the chance that hurricane goes and hits a particular city, you can now maybe actually calculate that more precisely. Okay, so I want to switch gears now and talk a bit about some of our results for climate modeling. So this is really taking the approaches that we looked at sort of previously for modeling weather. Weather, you only need to model the atmosphere is mostly enough to model weather. For climate, you need to model a lot more. And what we've done is, again, we're going to compare things to atmosphere only climate models. So that makes things a little bit simpler. We're not to be very clear, we don't have a complete climate model here. We are going to be forcing our sort of our hybrid atmospheric model with boundary conditions that from the observed sea surface temperature and sea ice concentration. So we're giving a lot of sort of information about the some of the large scale weather, including like some of like the global warming trends, for example, are basically that's in the sea surface temperature data. And so, well, what can you do with this? Well, for some of these models, what we've been able to do is we can take them and we can run forecasts going not just for a few days. We train the model for, say, a 3-day weather forecast, but we can also run it out for even longer. So here, for example, what I did is I ran a simulation of again like a weather simulation again with over the course of an entire year. And what you see here, even for something like the global average temperature, you see there's a fair amount of variation. The variation here reflects the sort of the up and down by some fraction of a degree. These are different weather patterns that sort of just basically happen to happen, and it's like sort of reflecting the chaotic nature of weather and climate. So if you want to make, say, a climate forecast, one way to do this is take this model let's run it a bunch of different times, and to do that, we can do that either by perturbing the initial conditions using that stochastic model. You can use it just by starting a weather forecast on like a few days later, and it sort of quickly diverges into something different. If you do this a bunch of different times, say 30 different times, you get 30 different projections of sort of what the sort of weather might look like over the year. You can average these, and now you've got an estimate of this. Now it starts to look like now you have something like a projection of what average temperature could look like, sort of averaged across all these models, and you can also compare it to observations. And so in this case, for example, compared to ERA5, that's our training data set. Again, this is sort of not the time over which the model is trained. So it's kind of going out into the future. Sort of we train the data model through 2019. So 2020 plus is sort of is after the training period. So we're not this isn't what the model is trained on. And what you see here is that, again, the sort of similarly, the observations have they match the trend pretty well. Kind of our average projection is actually pretty spot on, but also just as critically, the variability is about right as well. And so in the real world, you have these sort of the uncertainty of sort of like the different weather patterns coming through that are sort of similar to the sort of uncertainty that we get from our model from Neural GCM. So let me show you now kind of a couple comparisons we've made to different types of climate models. And so what the first model that we compared to, again, is sort of running this out, this sort of the simulation out for kind of like train through the sort of like run it out for 2020 and sort of compare, see how the results compare. So here we compared to a model from the NOAA's Geophysical Fluid Dynamics Lab called XShield. This is a model that's very similar. Basically, the numeric. Basically, it's it's NOAA's sort of FV3 GFS model, which is their operational weather forecasting model, except that it has been tweaked to run at a much higher resolution. So it runs at a 3-kilometer resolution, which means that it's a sort of a storm resolving model, and sort of in principle is able to simulate a lot of processes like convection directly instead of requiring parameterizations. So it's generally believed to be more accurate for modeling, again, for sort of representing sort of like the state of the atmosphere. And here, this XShield is also run in kind of a atmosphere only mode based on observed sea surface temperatures. And so remarkably, even though our simulation is on a much coarser grid, here we have a 140-kilometer resolution version for neural GCM, the error that we have for representing, we actually have a much sort of significantly smaller error, about a 40% lower error for the sort of total precipitable water in the atmosphere on average over that year compared to the XShield model. And again, these models like XShield are actually today are sort of incredibly expensive to run, actually impractically slow to run. We can run this simulation in simulates about 70,000 times faster than real time. This simulates only 20 times faster than real time, and it's actually about 1 million times cheaper to run neural GCM to simulate a year than for XShield. So XShield, we actually literally only simulated 1 year of data with this model currently, because it's so expensive to run a forecast. And these models they're more expensive. They're also harder to tune. So for sure, XShield could. I'm sure that if they ran XShield a bunch of different times and they're sort of optimizing these properties, I'm sure these results could be improved. But this is just kind of a taste of kind of what you can get with these AI techniques that really tune all the details automatically for you. And we can also do so again, looking at this 1 year forecast, we can also compare. We don't just do sort of the average climate properties. We actually, again, are producing realistic weather scenarios. And so here I'm comparing tropical cyclone trajectories over the course of a year with sort of observed tropical cyclone trajectories from ERA 5. And it's not a perfect match, but it's pretty close. I think in terms of the amount, you never would expect to get tropical cyclones at exactly the same places, but we're seeing cyclones in when hurricane season starts, we see a bunch of hurricanes in the going through the Caribbean. So we also see hurricanes and again in different parts of the world that are roughly what we'd expect. So that's very encouraging. And then I'll note this is sort of not a completely solved problem yet. We did kind of cherry pick the models that we are showing results for here with neural GCM. Sometimes our models still have some of these instability and climate drift problems that sort of previous hybrid models had. We haven't solved it completely, but in particular, they can, for example, sometimes a model runs for some number of years and then it just kind of blows up, or it sort of slowly accumulates some small bias in the temperature. And maybe it drifts out of distribution. And these are things that the model is not. We never trained the model for predicting, 25 years into the future. So it's a challenging thing to fix in the way that we build these models. We have a lot of ideas we've been sort of exploring on this, but I just want to again clarify that over longer time periods, it's sort of not entirely stable, 100% stable. But for the models that are stable, they still produce this realistic weather variability, even when you run them out for decades. And you can compare these trends again to atmosphere only climate models. Here we compare to these AMIT models, which are the atmosphere only configurations of sort of standard sort of production climate models. These are much faster than the XShield model that I showed earlier. And so with these models are the sort of like the current projections that the same atmospheric models that go into CMIP. And if you compare the average across here, we compared an average across so 30 different initial conditions for neural GCM in blue here, and then 30 different AMIT models in red here. And the average performance here much more closely tracks the observational record for neural GCM compared to these sort of production climate models. Now, to be clear, again, in this case, actually, this is over the period over which we trained the model. Of course, climate models are also sort of tuned to observations. They're definitely not tuned as heavily. There's some other caveats as well, but we think this is pretty encouraging, especially if you look at, for example, if you look at like the average errors, the spatial errors of these models for the neural GCM versus some of these AMIT models. Some of these models are just they're just too hot or they're too cold, and like actually every one of our sort of ensemble members here has a lower error than every single one of the AMIT models. And on average, the errors are about sort of 3 times smaller in terms of like the bias for temperature over those 30 years. Okay. Yeah, and it's again, a lot cheaper. All right. So with that, I'm going to kind of sort of wrap things up. I'm going to kind of come back and talk about some of the bigger picture. So oops, did I muted there for a second? Hopefully I'm back. Not sure how that happened. Okay, so I'm going to talk about the bigger picture. I'm going to talk about and so one thing I would say is that I think a lesson from this work is, I think it's really important to keep in mind, is that this sort of for thinking about for weather and climate simulation, the choice of sort of how to do your modeling of sort of physics versus AI is really a spectrum. It's not a binary choice. And even if you look in and say within these pure machine learning models, there are some of these models like say Pangu versus GraphCast, they're like defining your model on a graph, for example, versus using a transformer that's a little bit more of an sort of an unstructured model that probably requires more data and sort of a bigger neural networks. There's some choice you can make there, even within the space of physics-based models. Sort of how many different physical processes you're trying to model. In a climate model, you need to model, say, details, say like atmospheric chemistry, for example, that are not important in a weather model. We have there's sort of a lot of possibility for where for sort of the models we can build, and neural GCM is sort of our attempt at sort of putting something in the middle. It's not the only version, but we think it's sort of an encouraging version of sort of hopefully blending together some of the strengths. And there's a lot of other variations of this as well. I think in my mind, it's actually a really interesting research space. We don't actually know the right balance. I think for weather prediction problems, it's pretty clear that the pure AI approaches can be very effective, at least for the large scale global weather prediction problem. But when we get more in direction of climate or sort of more like a physical understanding, we may want to models that lie more in the direction of physics. So we can hopefully with hybrid models, we kind of have the option to kind of bridge the gaps between the sort of like and make the sort of the most prudent choice for our particular modeling needs. Okay, so here's a summary of neural GCM. We made this hybrid machine learning physics model for the Earth's atmosphere, and that in some ways hits sort of state-of-the-art accuracy, both for the 15-day weather forecasts compared to the ECWF ensemble forecast, and our climate forecast that again compared to AMIP and a global storm resolving model that are also better in some ways. And more than just being a bit more accurate, they're way faster and cheaper. So by a factor of numbers like 1,000 to 1,000,000 times less expensive, and that opens the door to not only just like running these models much less expensively, but really making these these atmospheric modeling a much easier and sort of more accessible in general. So it's something that now you can do like on a laptop, just a single GPU. You can fire up a notebook. You can run run a climate. Any student can run one of these climate simulations pretty quickly using our open source code. And I think and it's compared to needing to fire up a supercomputer. And it's also relatively simple. I mean, again, in comparison here, we have something like 20,000 lines of code versus 400,000 lines of code in like a production atmospheric model. So we have a paper. It's we have a preprint right now on the archive, and we have open source code and documentation on GitHub. So please take a look and let us know what you think. The paper will be coming out in a journal, hopefully in the next month or so. I did want to close also by kind of mentioning a few kind of ideas for kind of like next steps, and then I'll kind of go into questions here as well. So first, so the kind of the unresolved challenges for AI climate modeling. I mentioned this before, but I think improving model stability is a really big one. We still don't know how to sort of reliably guarantee these models are going to produce stable results when you run them out for much longer in the future, and especially when you run the models at higher resolutions, it's harder to make them stable. What kind of more can go wrong? Second challenge is figuring out how to couple into other components of the Earth system, and this is really important for climate because the ocean and ice and land and chemistry are all these processes are really critical parts of making climate projections, and they're very different from the atmosphere. They have much less data. They're much slower than the atmosphere. And so that's going to require a lot of creativity to figure out how to model these other parts, sort of maybe taking other sort of likely taking other physics-based simulation approaches, or at least this training data, or incorporating them directly in models in order to model things like oceans. That's where a lot of the memory in the climate system is. This is a really clear sort of challenge here is we're kind of reaching the limits, I think, of what we can do with these reanalysis data sets like ERA5 and for both the weather and climate applications. And so figuring out how to make use of more direct observational data sets like data from satellites is really key to making progress in this field. And lastly, another big challenge, especially in the climate context, is figuring out how to train these machine learning models in a way that should extrapolate and allow us to make projections even into, say, a much future warmer climate that is a place where we don't have training data. And again, there's some folks in the field who have been sort of starting to explore this, but I think there's still a lot of work to be done to figure out how to do this effectively. So with that, I will close again by sharing again details about where you can find out more about Neural GCM.
Great. Thank you very much, Stephan. Very interesting and very clear. I'm sure there's still questions. Floor's open.
Yes, looks like there's a question in the chat already.
Yeah, I'm going to read it out to you from Hi Freddy. Very nice talk, Stephan. Do you understand why the improvement for the ensemble simulation is much smaller than the improvement for the RMSE when comparing our AI approaches and ECMWF forecasts?
That's a great question. So I think I mean maybe I can go back to this, but I think the answer is that, and we've seen this now. If you look at, I think that some of the models like GraphCast, for example, you saw GraphCast was a little blurry earlier, and that's because GraphCast here is a deterministic model. It was optimized for a 3-day forecast. And so it was, it's kind of hedging its bets. It's kind of part way to making an ensemble prediction. It's doing predicting something closer to the ensemble average. So it's easier to cheat with the AI methods because they're optimized directly, for forecast accuracy. So I think so, and there's been yeah, and so I would say that's my guess, is that like the actual level of improvement from that you'd see, especially if you look at over a shorter time period than 10 days, it is actually more comparable for the ensemble prediction models. I mean, again, the range of like 5 to 10% sort of than like the bigger gap that you see on a 10-day forecast.
Right, then Peter Watson asks, are there plans to make a stochastic model potentially important for capturing things like extreme weather events?
That's a good question. So we actually, I think maybe this was not really entirely clear here, but we do in fact actually have a stochastic model with neural GCM. That's kind of we actually, I'm a little bit of it in the weeds here, but we built some trained both deterministic and stochastic models with neural GCM. And the way that we did that was by injecting this sort of correlated random noise, these Gaussian random fields, sort of very similar in principle to how stochastic models at institutions like ECWF are built. We optimize it to based on sort of this probabilistic loss function, again, this CRPS metric. So we did in fact build a stochastic model, and I think I agree that's incredibly important. I think we didn't actually show, we weren't quite able to get the stochastic results quite as good for the climate projection in terms of the results in this paper, but we believe, I think, very strongly that like the stochastic modeling is the way to go in the future.
Great. Freddie has a follow-up question. Given your answer, then can we really say that the improvement is significant?
That's a fair question. I mean, look, I think that a 5 to 10% improvement in some of these error metrics, if you calculate something like how long is like what's like the useful lead time in a forecast with something like neural GCM, it depends on what you're doing, but it's something like the difference between a 7-day forecast and a 7-day forecast plus 6 hours. So is a 6-hour lead time impressive over the best forecasts? I mean, I think practically there's not a whole lot more. I mean, maybe you can do it an extra 6 hours. I think it's important to think about this in the historical context here, which is that like the rate of improvement here. And if you compare the rate of improvement that we've seen with these AI models to the rate of improvement with the physics-based approaches. So, I mean, it really had these models with like sort of close to state-of-the-art accuracy over just the past couple of years. So maybe we can, maybe in 5 years we can come back here and say and judge if it's made a difference or not. I think there's still a lot of interesting sort of exciting ideas, especially like stochastic modeling. There's a few other stochastic models that have come out just recently in the past few months from like DeepMind and ECWF, and so like there's a lot of people looking into how to like train models using observational data instead of reanalysis. I think there's still a fair amount of relatively low hanging fruit for AI models.
Great. Next question. So, I mean, folks, you're also welcome to just unmute yourself and ask the question, but I'm also happy to read out your question. It's fine. Dennis Sergev asks, could neural GCM reproduce the butterfly effect? If not, does it mean it has unlimited predictability?
That's a great question. I will say we haven't done a really detailed study of the butterfly effect, and it's actually like a pretty nuanced question if you try to look into, like, there's kind of a few different versions even of what the butterfly effect is. Tim Palmer has like some like a nice like paper on this, or actually in his book. I would say we definitely do not have unlimited predictability. I mean, we are definitely absolutely not all the fundamental challenges in terms of the unpredictability of weather, sort of beyond the sort of predictability timescales for weather forecasts are still here for neural GCM. It's just it is an incremental improvement, but it has not resolved the fundamental challenges of predictability.
Max.
Yeah. Hi, Stephan. Thank you very much for this really great talk, and overall also this really great project and the paper. Congratulations also to that. I'm mostly interested in climate simulations. So maybe I'm asking now a little bit of a more mean question because obviously also working on this myself, I know the stability of these models is a huge problem. And you also said this already also in your talk. It's a very hard thing to accomplish, to have like decadal stability with these models. And this is also very deeply connected to what you initially showed, to the blurriness of the predictions that also these models make. And I've seen also in the paper that you integrate, for example, a spectral loss that probably also helps with this, because I think, at least my opinion on this is that basically the hybrid model, or like machine learning model, not conserving the spectrum and the energy is probably one of the main causes of this. So I'm a bit interested in, first of all, if you agree with this and what your impression on this is, and if you actually also for neural GCM checked the energy conservation for more than just a year. In the paper, do you do this for 1 year only for like the seasonal cycle, but also if you do this, check this for like longer simulation, what your impression is, also for example, if just integrating explicit constraints could help. And yeah, what your opinion on this is.
Thanks. That's a very insightful question. So I'll say, first of all, I totally agree that like this blurriness, I think, was is one of the major challenges with instability, and that when we, in the process of developing this model, when we figured out some different training strategies, like some different loss functions, and like stochastic versions of our model that avoided the forecasts would not only became less blurry, they also became much more stable as well, and that happened like kind of at exactly the same time. And I think that's again because the blurry forecasts, blurry models are actually the blurry state of the system is like out of distribution from what the model is trained on. And so if you can engineer your training setup so the model is not rewarded for being blurry anymore, then that really helps. In terms, I mean, I would say that the most, it definitely is still a major challenge. I think that integrating constraints may be an effective way to solve this. I'll say that our experience with constraints, I would say, has been a little mixed, in the sense that sometimes I guess the truth is that we haven't really tried too hard to say that we have to integrate like an energy constraint in the system yet. I mean, that would be a relatively straightforward thing I think to do. I mean, well, maybe a little complicated, but in principle that could be done. You could use kind of similar numerical techniques to what were used in conventional climate models. I think that again, it's also worth keeping in mind that like it took a lot of work to make climate models stable for doing decadal prediction in the first place as well. So maybe it's okay if it takes a little while to catch up on these AI methods. And there's certainly a lot of ideas from that have been developed for climate models that I hope are also useful for stabilizing the AI models.
Thanks. Any further questions? Maybe let me sort of related to this. Let me also ask a question. So you showed this the climate the warming trend and how neural GCM reproduced that. How does this and this was sort of in an AGCM setting, like an AMIP setting.
Yes.
So the model, it's not a climate model in the sense of it sees CO2 and this kind of stuff, right? It's a circulation model. So does it see SSTs?
It sure does see surface temperature, and if we didn't see SST, there's no way that we could capture this. So there's no carbon dioxide in this model. There's no there's no source of memory beyond the atmosphere, for example. So there's absolutely no way that we could get this without knowing sea surface temperature.
Yes. So, but it does at least, and this is already, I think, not trivial. So would you say it does learn the response of the atmosphere to the SST forcing in the right way? That's what we should.
That is mostly true. I will say we just did a few studies in the paper where we tried artificially increasing sea surface temperatures, for example, and we found pretty reasonable behavior when you increased a couple of degrees Celsius. When you increased 4 degrees Celsius, that seemed to be sort of beyond the bounds of the training data, and the model did some pretty strange stuff. So to some extent, at least, we seem to have learned the right response to sea surface temperature.
So this would mean that you still, due to the neural network component of the full hybrid model, you still have an out of sample problem.
There's definitely, we think that potentially fewer out of sample problems than like kind of a full emulator approach, because we take this kind of column local approach with our neural network, where it's doing a lot less modeling. It's kind of only modeling kind of these like residual terms in a local to a grid cell. But and that means that you kind of effectively have a much larger sample size from looking at observed weather. But we absolutely still have some of these generalization challenges, and that's something that we didn't really try to tackle in this work, but is definitely something that'll be important to tackle in the future if we want to solve climate projection challenges.
Yeah. Cool. No, but it could be worse, right? It could be that you wouldn't have any trend.
Yeah.
Yeah. So yeah. Cool. Right, Freddy.
Thanks so much. The talk was very interesting and the work is amazing. So I would like to come back to the perspective you gave to make a climate simulation in the sense that you want generalization, for instance, when changing the level of carbon dioxide or other things. So what do you already have a guess of what would be the best architecture for this? I mean, is it neural GCM that is the best way to do this with an hybrid approach, or is it something else? Do you have a guess for this?
That's a great question. So I think there are two approaches that might work for this. And I guess also I think maybe to be clear, I haven't really didn't really mention it here in this talk, but there are actually a few approaches recently, especially there's a model from Chris Brotherton's group at the Allen Institute that has been exploring sort of pure AI models also for sort of for atmospheric simulation for climate as well. And they have some I think pretty promising results there. Not so it's possible that we'll be able to get some of these pure AI models to work well for doing some of these stable, for example, for doing like climate simulation. I think they're kind of two approaches and that seem promising, and both are going to sort of rely to some degree on simulation. So the one approach, and this is the approach I think we've been seeing like folks in like Chris's group and elsewhere have been doing, is using simulations as ground truth. So running climate projections, say with CMIP models, and now you have a bunch of examples, and now you train an emulator that is potentially, say, much faster. It's not going to be more accurate than the simulations because it's trained on the simulations, and climate models have a lot of issues, but potentially you could train those simulations and then refine the model, sort of pre-train on simulations and sort of fine-tune it, refine it on like observational data. And that could potentially work pretty well to kind of help give the model, so the model has at least seen examples of what happens in, say, in some future climate scenario, even if you want to actually tune it based on observations. I think you can also take scenarios where even say in a climate, there are some cases where some of the large scale, there's behavior the model should have, even that we know kind of ahead of time pretty well, even without sort of exactly matching a simulation. So we know, for example, that kind of no matter what, if you increase, no matter how, that we believe that the climate should be stable, for example, even if we increase the temperature by, say, 4 degrees. And so you could force, and also that we believe that the temperature should, so you should in principle be able to run the model out for 100 years, 1,000 years with, say, a constant repeating sea surface temperature, and it should also show a constant cycle as well. So some of these constraints, I think you could sort of it's not entirely clear how to use it as a training loss, but I think that those are that's one way to kind of, again, tune a model without observations, sort of based on our physical knowledge. And the last option, which maybe I'm a little more partial to, because it's similar to what we did with neural GCM, is you could think about building in more of the physics-based simulation components from the climate model. So, for example, in principle, right now we have kind of a black box sort of full parameterization with a neural network. We could break that out into more detailed physical processes, and we could, again, hypothetically, have incorporate a traditional radiation model inside of the, compatible with say a neural network maybe that does clouds and precipitation. And so that's a way that you could have the model still, really have a very, say, constrained response to carbon dioxide, for example. If that's something that we like really wanted to be sure was handled properly.
Thank you.
Peter.
Yeah, thanks again, Stephan. Yeah, just wondering, so for climate work, it'd be very interesting to have a model which, is trained on, decades further back in time than what you're showing here. So I wondered, are there plans to extend the training data back, back to, say, like 1950, around the start of Era 5 or say?
Yeah, so so Era 5 does go back to, the Era 5 is back to 1940. The quality of the data in for sort of the pre-satellite era for Era 5 is much worse. So from a weather forecasting accuracy, that was not helpful. We actually only trained it back to 1980 in this paper, although we had the older data. I think that this is something we do want to come back to. I think that the biggest challenge, honestly, that we're trying to figure out right now, maybe a couple of challenges I'll mention. The biggest one is the stability challenge. So we really, like, one thing we found pretty frustrating is that we weren't able to make our highest resolution models stable for doing, say, a climate projection. So the multi-decadal simulations were with a model that was like a 2.8 degree model, which is still pretty coarse. We would much rather be doing things with one of our models, say the 1.4 degree model, which is like twice the horizontal resolution. And so I think once we get a better handle on stability challenges, it makes it a lot easier to build these models in general, instead of having to I don't know, we probably trained a dozen versions of the of that longer term model. And then we took the one that had like, in general, that had sort of generally the most sort of stable results. And we used that in our for the results in the paper. So it's again a little cherry picked. I think we would love to be able to have sort of more reliable models first, and then we'll kind of look into how we can kind of expand the training data set and so forth.
Just on the instability aspect, I can think of various things that would be interesting to do with a model which could just do like 1 year runs, just done at different points in time or something. So, I don't know. It's not clear to me that it's such a showstopper to have this instability. But
yeah, I agree. I think we already have something we already have a model that models we have some models that can be very reliable, for example, for 1 year runs. And we've found, for example, that even very simple things, like, I'll say that we've experimented on this, but like, we train the model because especially with these stochastic models, they still have the right loss function. Even we can train them for as long in the future as we want, in principle. So we can train them to make a 20-day weather forecast. And the model is still, at that point in 20 days, you're mostly just learning the right distribution of weather. You're not trying to predict, you're not trying to make a weather forecast, really. And the performance of the model and the stability increases, somewhat significantly. So I'll say that is kind of so we're still, I think there's a lot that can be done to kind of further improve that. And at some point, it's going to be good enough. And I think we're hopefully pretty close there.
Thanks. So we're already 11 minutes over time, but so as long as you're with us, Stephan, I think people are going to ask questions. Michael asks, have you tried using SGS noise to test stability? I guess SGS stands for subgrid scale.
That's a great question. I would say, so I think the answer is no, we haven't explicitly tried that, although we do, again, these like stochastic models, which again are more stable, we are injecting this sort of multi-scale noise, which does include some components that are at the subgrid scale.
And maybe let me ask a very quick follow-up question to Max's question earlier about stability and energy conservation and so on. In your answer, if I understood correctly, you said that you're sort of building up blurriness with neural GCM as well. I totally understand why that happens with GraphCast, Fangu, Pengu, and so on. Why does it still happen with neural GCM? Sort of, if it would just be the GCM, it wouldn't.
Well, so it's not, I guess I would say that the model, I don't think it's the blurriness really that breaks, that causes stability issues necessarily. I think sometimes the blurriness, like, it's other way, like the model kind of anytime the model kind of drifts out of distribution a little bit. And this is something that's actually kind of a pretty common issue. In machine learning type problems. This is something that comes up actually in self-driving cars. If you want to train a self-driving car to drive on a road, and you say just copy an expert driver, like always make the same decision as a human driver. That works pretty well for like the first, like for making like one decision. But when the car's made 10 decisions, and then it like very quickly encounters a situation that's very different from what a human driver did, and that's when it makes a mistake. And again, it makes but yes, I'd say we have had versions of, again, the hybrid models is not necessarily directly a fix, I would say, for the blurriness issues. I think that is maybe partly due to the hybrid models, but I mean, but also a lot due to how we've sort of formulated the training setup and the losses. So there, again, these stochastic models, like we have stochastic, like that, the stochastic models really fix that. The other thing, we also had approaches that we explored in the paper where we, and probably the best one, I do have one backup slide on this, but kind of all like how we tuned the deterministic models. We also did this trick, which turned out to be really important for making better deterministic models, which is that you don't penalize the model for getting small scale features wrong far into the future. Because it's impossible to predict exactly where that cloud's going to be 3 days in the future. So instead, only have a penalty on the very large scale weather features. And this is pretty straightforward to do with just by applying a spatial filtering or like a blur, basically. And so when we applied these sort of blurring filters, the model learns, like the model actually. So we blurring filters both to the predictions and the ground truth. The model was able to make much sharper, sort of learn to make much sharper predictions because it's not being penalized for making a sharp prediction when and it makes a weather forecast. So there are a lot of different tricks, I think, even for deterministic models to sort of mitigate the issue, these blurriness issues. But I would say that that's definitely, again, was a. I mean, honestly, is like a separate issue than I think not just about the hybrid modeling aspect.
Right. All right. Any final questions? Okay. If that's not the case, then again, thank you very much, Stephan. That was very interesting, and also congratulations on the whole project. Really cool.
Thank you.
And then so we are going to have another series in July, I think, but then we're gonna have the summer break. So in July it will be David Nealon again at 9 a.m. Los Angeles time. That will be the first Monday of July, which will be July 4. And hope to see many of you there. Have a lovely rest of the week, and thanks again, Stephan.
All right, take care.
Okay, thank you.